If you're multiplying two binomial expansions together, chances are you're going to end up with a lot of terms. So unless it's a fairly manageable sort of question, you're probably not going to be asked for the full expansion. It's more likely that you're going to be looking for individual terms. But if you did need to find every term, how would you go about doing it? Well, a table would be super helpful. Let's look at a simple example here. We've got x plus 2 to the power of 4 multiplied by x minus 1 cubed. Now, we can generate the expansions for each of these without too much trouble. So this one's going to have 5 terms, and here they are. And this one's going to have 4 terms, and here they are. Now, when we've got smaller expansions to do, we often use those lines to say, right, I've got to do this times this, and this, and this. And we use those lines to keep track of what we've multiplied by what. But you can see that here, there's going to be so much multiplying to do, it's going to get really messy. So a table is super helpful. I've put the 5 terms from the first expansion along the top and the 4 terms from the second expansion down the side, and that way I can clearly and easily multiply each term by each other term. So you could go through here and say, all right, multiplying these, I've got x to the power of 7, I've got 8x to the power of 6, and it's quite straightforward just to write your lists. Then you could quickly and easily see which ones are like terms and add them together so that you can come up with a nice list as your full expansion. Now, if you're just looking for an individual term, let's say you want to find the term in x cubed from this question here. A table like this, if you've already got these expansions worked out, and these are fairly easy to come up with, could be helpful because you can clearly and easily see what needs to be multiplied by what. If I want x cubed, then I'm going to need to have x cubed multiplied by a constant, no x's at all. So I could clearly and easily see I'm going to need this box, so I could work out what it is. So I need that one. I'm going to need x squared multiplied by just x to get my x cubed. So multiplying these two, I can easily see that I'm going to need this box. And x is going to need to be multiplied by x squared to get my x cubed. So multiplying these two is fairly straightforward. I need that one. And then here I've got a constant. I'm going to need to find the term in x cubed and multiply those together. Now I've found 4 terms that are all in x cubed. If I add these up, I'll have the complete and finished version of the term in x cubed from this whole question. Now, we don't want to do any more work than we have to. So some people looking at this method would say, well, I've come up with all of these terms here, and perhaps they were quick and easy to do, but there was quite a few that I didn't really need. There's combinations I don't need. Whatever method works for you is a good method because it needs to make sense. And even if you don't actually use this method, just looking at the table and visualizing what needs to be multiplied by what might be super helpful. Let's have a look at now how you can do this without actually generating these expansions and instead just looking at each individual term that you'd need and generating the terms individually. If you prefer this method, go for it, but having a look at both I think is quite helpful. Now, most of the questions you get that involve the product of two binomial expansions probably won't be as complicated as having to look for many different terms and adding them together. Often they'll just say, find the constant term from an expansion like this. And be warned, these numbers might not be 4 and 3, they might be really large numbers. And so we're going to have some good strategies in mind. I think this table concept helps because we're imagining what we need from each part so that when they're multiplied together, we get what we want. Now, another way to set out that same question would be just to consider the combinations that you need. You either need a constant in this section multiplied by x cubed in that section, or x times x squared here, x squared there multiplied by the x there, or x cubed here multiplied by the constant there. And then it's a matter of working out what each of the individual terms are. Now you'll notice that here we're actually finding all of the terms in this second expansion. I've just written them going upwards in this direction or downwards, however you like to see it. And the way I've written these terms out here, I have most of the terms, but not all of them, because to find a term in x cubed, I actually don't need x to the power of 4, because that's not going to help me. So I've got most of the terms from both the expansions in there, but the setting out is different. Now, choose the way that makes the most sense to you and leads to the fewest errors and the quickest and easiest method. Both methods involved finding those 4 terms and adding them together, and the term in x cubed was minus 16x cubed. In this example, I need to find the term that is independent of x, in other words, the constant in this expansion. Now, again, there's a number of ways that you can do this, so go with whatever you feel most comfortable with. In this example, I've just decided to expand the whole thing out. So I've put a line of working. Once you're good at this, you might jump straight to finding each individual term in your head, but I've just been really safe and careful here, and I've written down my method for finding each term and then what each term is. So leaving that step out or doing it in your head is up to you, but if you're getting them wrong or it's in any way confusing, sometimes it's actually just quicker to write it out and then jot it down and you can be sure of it. Now, what you'll notice is that the second part here has got the pronumeral in the denominator. So what that means is that all of these expansions have their pronumerals down the bottom of the fraction. So it's when they multiply only with the term that has the same power of x in the numerator that those are going to cancel out and make a constant term. So I don't need the whole expansion of everything times everything, and I haven't bothered drawing up the big table, but I'm imagining the table and I'm thinking, well, I need this constant to be multiplied by the constant. That will give me a constant. If I've got a term in x and I can multiply it by a term that has something divided by x, the x's will cancel in that term, and that will just give me 6x multiplied by negative 80 over x. Now they multiply together to make negative 480. So you'll notice here I've multiplied these two terms to get my 32. I've multiplied those terms, the x's cancel, I get minus 480. I've multiplied these two terms, x squared and something over x squared, to get my 960, and these two terms will give me minus 320. Now there's no point going any further. These two terms don't have a corresponding term in the other expansion that's going to cancel out their x's. So they're not going to give me a term that's independent of x. So I've only got 4 of them. I work out what they are and I add them together. Now again, there's quite a lot of work that we had to do there, but by laying out all the terms, sometimes it's quicker and easier because you can see exactly what needs to go with what. Another thing you could do in a question like this to save yourself some time is to realize that there's going to be a pattern. And once you start seeing that pattern, you can think, well, I'm only going to need to go as far as I need to in this expansion until I've got things that are as big as what I'm looking for. So you might have got to this point and then put plus ... knowing that it didn't really matter what came after that. And those sort of strategies can save you some time. In here you'd have plus ... Sometimes it won't make sense to expand out an entire binomial expansion because you'll realize quite early on in your question that you only need certain parts of it. So in this example, we need to find the coefficient of x in this expansion. Now this part's just got 3 terms in it, and they're not raised to any power at all. And we're multiplying by a binomial expansion that's got a power of 6 here. So thinking about how I can get terms in x, I either need to have a constant from this part multiplied by the term in x here, or the term in x here multiplied by the constant there. There's really no other option because neither of these has got any fractions with x's on the bottom. So if all I need is the constant from here, I can see that that's 2, and then I'm going to need the term in x from this part of the expansion, or I'm going to need the 4x multiplied by the constant here. So I can work out both of those and then add them together. So for the first part here, I've got 2 multiplied by, now the term in x here, remember our little recipe for finding the, let's use 3 here. So we're making it more specific, and in fact n is 6, so we can put that in. Now if we want x to be x to the power of 1, then that means that r has to be 5. And starting off with your little recipe over like that, sort of in your margin, is a really handy way of showing your working without actually putting it into your line of working. But an examiner can clearly and easily see what you've done there. So 6 choose 5, that's just 6, multiplied by x, multiplied by 3 to the power of 5, 243. That will give me that term. So I've got to multiply 243 by 12. So what we're going to get is 2916x. Or I could have 4x multiplied by a constant. So the constant over here is just going to be the last term of the expansion, which is literally just going to be 3 to the power of 6. So I need 4x times 3 to the power of 6. And that gives me the same answer, actually, 2,916x. So when I add those x's together, the term in x, make sure you always answer your question by being really clear, is 5,832x.